So now that we know how area of a region can be computed using a double integral, and that was by just setting a horizontal plane at a height of 1 above my region so that the volume underneath that plane is numerically equal to the area of that region. But then you might say, well, wouldn't I also be able to, over a region, instead of setting a horizontal plane at a height of 1, if I set that horizontal plane at a different height, then what I'm going to get is going to be a scalar multiple of the area of my region. And that might happen in applications if, for example, I have a material made of a uniform density and a uniform thickness. So maybe I know that the weight of my piece of paper is 24 pounds per cubic foot or something like that, right? And so if I integrate the number 24 over my region, I'm going to get 24 times the area of my region, which might correspond to the mass of my region or something like that. So this function that we integrated, this 1, in the case of getting an area, is kind of a stand-in for something that we can allow to vary if the material out of which my two-dimensional region is made varies in density. So that function we're integrating might be called a density function. And if that's a density function, density is defined as the mass of something per unit area in this case, or per unit volume if we do a triple integral, as we'll do in a couple of days from now. That density function can kind of tell me how dense is this material at each point inside of my region. So that when I integrate, what I'm integrating is the density, which is mass per unit area, multiplied by dA, which is a unit of area. And so this integrand is going to have units of mass. So that when I integrate that function over my region, what I get is the total mass of the region in total. So if the density of a region like this half circle here is given by delta of xy is equal to x, in other words, the density of my region right along the y-axis is not dense at all, it's equal to 0, and the material gets more and more dense as we go out further to the right. So the density as we get all the way to the right end here is going to be 3, I don't know what our units are here. It doesn't give us units. So maybe when you imagine that it's grams per square centimeter or something like that. So the density increases as we get closer to this edge. Then we can use a double integral to compute the mass just by integrating this density function over this region. And so let's take a moment to do that. This is also going to be a good exercise for us, I think, in doing a double integral in rectangular coordinates that is going to be a little bit messy. And then it might be easier for us later on to do this integral in polar coordinates instead, because the region over which we're integrating is a piece of a circle. And circles are polar coordinates specialty, and they're sort of an awkward thing for xy coordinates to describe. So your first task is going to be to figure out how to tape measure up this region D using xy coordinates, and then to set up and evaluate an integral that will compute the mass of this region if its density function is given by delta xy equals x. So it's pretty straightforward calculus once you get it set up, right? That you tape measured this half of a circle and found that the most convenient way to do that is to describe it as a type 2 region, because it's the right half of a circle of radius 3. That means we can bound the left side by the y-axis, x equals 0, and the right side by the equation for a circle of radius 3 centered at the origin solved for x, right? And so you get x equals the square root of 9 minus y squared. Would be an expression for the right-hand side, 9 minus y squared, of this region. Right? So as a type 2 region, this is much more straightforward to describe. I mean, you could have described it as a type 1 region, but then both your lower and your upper limits would be functions of x, and they would both have these square roots, so square root of 9 minus x squared and minus the square root of 9 minus x squared. Anytime you can have a 0 as one of your limits, it's probably always a friendlier thing to do if you can get away with it. So then your integral is, because we're finding the mass where the density function varies with the x variable, then we're integrating x with respect to x and then with respect to y. And so after one step, x squared over 2 is the antiderivative, and evaluate that at square root of 9 minus y squared, and then at 0, and subtract. The new integrand is then 9 minus y squared all over 2, integrated from negative 3 to 3, and we get a mass, a total mass for this lamina of 18 grams, or whatever units we happen to have put on the original density function.